Today we're going to look at a different type of improper integral. Last time we dealt with integrals that went from some finite number to infinity, or from negative infinity to some number, or from negative infinity to infinity. Today, we're going to deal with what happens if our y values over the interval we're trying to integrate over go close to infinity or negative infinity. And really what this is going to involve is integrating on intervals that contain vertical asymptotes. So, to integrate an improper integral on an interval containing a vertical asymptote. And for all these examples, we're going to say our function f of x has a vertical asymptote at x equals c. First case, if I want to do the integral from a to c, if I want to integrate up to that vertical asymptote. So this would look something like this. I've got a, I've got c, and I'm going to put a vertical asymptote at x equals c. I've got some function getting close to that vertical asymptote, and I want to try, if possible, to find this area over there. Well, instead of integrating right up to the vertical asymptote, because I can't really handle that, instead, I want to do the integral from a to b of f of x. And I want b to get really close to this vertical asymptote. Well, to do that, I'm going to set up a limit. I want b to get close to c. But not just c in general, I need to get close to c from the left side. I don't care for this particular problem about what's happening on the right of c, just what's happening to the left of c. So I'm going to turn my problem into a limit that looks like that. Second case, if I want to integrate from a vertical asymptote to some number, from c to b of f of x dx. So vertical asymptote there, finite value there, I've got some function looking like this, and I want to try to find that area over there. Again, I'm going to set this up as some limit. Instead of going from the vertical asymptote to b, I want to go from some constant a to b of f of x dx, and I want that constant to get really close to this value of c. I'm going to do the limit as a approaches c, but again, I'm going to make it a one-sided limit because I don't care what's happening to the left of c, only as I'm getting close to c from the right side. I'm going to make it the limit as a approaches c from the right of the integral from a to b of f of x dx. There's one other case. If we want to do the integral from a to b of f of x dx, and this is an interval that has a vertical asymptote in the middle of it. So let's say I have something like this, and I want to go like that, and I want to go like that, and I want to try to find, if possible, that shaded area. Well, just like what we kind of did last time, where we had the integrals from negative infinity to infinity, I split it into two different problems. I'm going to do the same thing here. I'm going to do the integral from a to c of f of x dx, plus the integral from c to b of f of x dx. Then to deal with that first one, I'll use ideas like in number 1, and then to deal with the second one, I'll use ideas like what I have in number 2. So I want to show you 3 examples of using these, and that's what I have here. Let's take a look, for starters, at the integral from 0 to 1 of dx over the cube root of x. I know that there's a vertical asymptote at x equals 0. So instead of going from 0 to 1, why don't I just go from a to 1? I'm integrating x to the negative 1/3 dx, and I want a to get close to 0 from the right side. So I'm going to say the limit as a approaches 0 from the right side. Now, I'm going to go and use my fundamental theorem of calculus on this, plugging in 1 minus plugging in a. This gives me the limit as a approaches 0 from the right of x to the 2/3 over 2/3 from a up to 1. That gives me the limit as a approaches 0 from the right of 3/2 times, I'll say 3/2 x to the 2/3. I'll leave it like that for right now from a to 1. Then I'll go and I'll plug in limit as a approaches 0 from the right, 3/2 times 1 to the 2/3 minus 3/2 times a to the 2/3. Well, I can certainly handle doing 1 to the 2/3. Can I plug in 0 here? Absolutely I can. So this will give me 3/2 times 1 to the 2/3 minus 3/2 times 0 to the 2/3. That's just going to give me 3/2. I got a finite value for this integral. Let me show you two more. Let's do the integral from 1 to 2 of dx over x minus 2 cubed. First thing I should probably do, though, is do a u substitution on this thing. So I'm going to say u equals x minus 2, and then du equals dx. And I'm going to turn this into the integral of du over u cubed. And now, since I am changing this into u values, I should also change my limits of integration. 1 will become 1 minus 2, or negative 1. 2 will become 2 minus 2, or 0. Once again, I have an issue at x equals 0. So I'm going to turn this into the limit as b approaches 0. I only care about from the left of 0. If you think how we're going from negative 1 over to 0, I just care about as I'm approaching it from the left side. Limit as b approaches 0 from the left of the integral from negative 1 to b of u to the negative 3 du. We'll go integrate. Limit as b approaches 0 from the left of u to the negative 2 over negative 2 from negative 1 to b. I'll clean that up a little bit and say the limit as b approaches 0 from the left of negative 1 over 2u squared from negative 1 to b. And that's going to equal limit as b approaches 0 from the left of negative 1 over 2b squared plus 1 over 2 times negative 1 squared. So over here, as I'm approaching 0 from the left side, well, 0 from the left is a small positive number. Squared is still a small positive number times 2 small positive. Negative 1 over that, negative 1 over a small positive number is going to be huge. I actually think I said something wrong. You're plugging in a small negative number, you're squaring it, you're getting a small positive, times 2 is a small positive. Negative 1 over small positive, huge. This thing over here is giving me negative infinity. I don't even really care about this part, although that part's okay. That part's just positive 1/2. You can't handle negative infinity plus 1/2. Therefore, we're going to say that this integral diverges. That one diverges. One more. Let's do the integral from negative 1 to 2 of dx over x to the 4th. We've got a vertical asymptote at x equals 0, so I'm going to split it and go the integral from negative 1 to 0 of, why don't I go straight to x to the negative 4 dx. And then I am going to do the other one as the integral from 0 to 2 of x to the negative 4 dx. And actually, rather than trying to deal with all of this, why don't I just do one of them, see what happens? If it works, do the other. Because if one of them diverges, I can just stop there and say the entire thing will end up diverging. Let me focus right now on the integral from 0 to 2 of dx over x to the 4th. I would love it if you could pause the video and give this a try and see what you get for this. Did you actually pause the video? Or are you just waiting for me to do it? Hopefully you pause the video. Let's go. I've got an issue at 0, so I'm going to say limit as a approaches 0 from the right, because I'm to the right side of 0 if I'm going between 0 and 2, only to the right. Integral from a to 2 of x to the negative 4 dx. That gives me limit as a approaches 0 from the right of x to the negative 3 over negative 3 from a to 2. Clean that up again. Limit as a approaches 0 from the right of negative 1 over 3x cubed from a to 2. That is the limit as a approaches 0 from the right of negative 1 over 3 times 2 cubed plus 1 over 3a cubed. This is fine, but I've got an issue over here. Small positive cubed, smaller positive times 3, small positive 1 over that. That part gives you infinity. Therefore, this thing diverges. Oops. Therefore, that thing diverges.